Lesson 6.1, Vectors in the Plane. This lesson has many standards we need to cover for this course, so there will be many vocabulary terms we go through, as well as many examples in this lesson.
I'm applying for a new film loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires live piranhas. Never seen one before? No, you haven't. I invented it. Do you want a demonstration? Oh, ow! Gosh, it's so difficult sometimes to get the black balance.
Now we need to discuss some key terms related to two-dimensional vectors. A two-dimensional vector V is an ordered pair of real numbers denoted in component form as a comma b. If we have these arrow brackets, that's indicating that we're referring to a vector. The standard representation of the vector a comma b is the arrow from the origin to a point AB in the coordinate plane. The magnitude of a vector V is referring to the length of the arrow, and the direction of V is the direction in which the arrow is pointing. Now we're going to relate some of that vocabulary to vectors in the coordinate plane. So if an arrow has initial point x sub 1, y sub 1, and terminal point x sub 2, y sub 2, it represents the vector in component form of we're subtracting our x values and subtracting our y values, finding those differences. So if we want to find the component form for vector rs, we know this is referring to a vector because we have a line above it with an arrow. So we have our initial point and our terminal point. We can tell this is the terminal point because that is the point that has the arrow at the end of it. So that also tells us which direction our vector is going. So if we want to find the component form for vector rs, we're going to subtract our x values. So -1 minus a -4, if we're subtracting a negative, that's the same as addition. And then we want to do the same thing for the y values, 6 minus 2. Now we just simplify this. -1 plus 4, we get 3. 6 minus 2, we get 4. So that is the component form for vector rs. If we use a similar process to find the component form for vector OP, we would simplify to get component form as 3, 4 as well. So even though these vectors have different locations on the coordinate plane, they have the same component form, so these two vectors are equivalent. Next, we're going to work with finding the magnitude of a vector, which we said earlier is the length of the arrow that represents that vector. So essentially, if we have 2 points representing, one is the initial, one is the terminal point of a vector, all we have to do is find the distance between those 2 points, so apply the distance formula. If we take the absolute value of v is essentially what we're doing to find the magnitude, that is our notation we use for the magnitude of a vector. If we're given the component form of a vector, then to find the magnitude, all we have to do is take the square root of our x value squared plus our y value squared. Now we're going to go through an example of finding the magnitude of vector v, which is represented by the segment PQ. P is the ordered pair 3, -4, and Q is the ordered pair of 5, 2. So if we want to find the magnitude of vector v, we're going to apply the distance formula to the 2 points that represent that vector. The magnitude of vector v is equal to the square root of 5 minus 3 quantity squared plus 2 plus 4 quantity squared, which we can simplify down into radical 40. We can simplify that further by breaking radical 40 up into radical 4 times radical 10, which simplifies to 2 radical 10. So the absolute value, which refers to the magnitude of vector v, is equal to 2 radical 10. That represents the length of that arrow representing the vector on the coordinate plane. Next, we're going to discuss vector addition and scalar multiplication, which is pretty straightforward. So if we have two vectors, vector u and vector v, if we want to find the sum of those vectors, all we're going to do is add corresponding components. So if we're taking vector u plus vector v, all we're going to do is add the first components together, and then we're going to add the second components together to get the sum of those vectors. If we're finding the product of a scalar k, a scalar just refers to some constant being multiplied by the vector. So if we're taking a constant k times vector u, essentially all we're going to do is distribute that constant through to both components. So we're taking k times the first component, and we're taking k times the second component. The drawing on the left just shows that vector addition is commutative. So if I would take vector u and then add to it vector v, or if I took vector v and added to it vector u, we're going to get the same resultant vector, which represents the sum of vectors u and v. Now we're going to go through an example that incorporates vector addition and scalar multiplication into the same problem. So we have vectors u and v, which we're given the component forms for. We want to find 3 times vector u plus vector v. The first thing we have to do if we're going to find the sum of 3u plus v is use scalar multiplication. Remember, we just basically have to distribute that 3 through to each component. So if we distribute the 3 through, we would get in component form for the vector 3u, 6 comma negative 3. Now we're going to add to that 5 comma 3, which represents vector v. If we're just adding two vectors together, we just have to add corresponding components. So we're taking 6 plus 5 to get 11, and then negative 3 plus 3 to get 0. So this is the component form that represents vector of 3u plus v. Next, we're going to discuss unit vectors. A vector u with a magnitude of 1 is a unit vector. So as long as we have a vector that is not the 0 vector, then we can find the unit vector by following this general process. So we can take our vector v and then divide it by the magnitude of that vector to find the unit vector. For an example, we want to find a unit vector in the direction of vector v, which has components 2, negative 3. The first thing we need to do is find the magnitude of this vector v. To find the magnitude of vector v, it's pretty straightforward. If vector v is in component form, all we have to do is take the square root of our first component squared plus our second component squared. So the magnitude of vector v simplifies down to the square root of 13. Now to find the unit vector, we're going to take 1 divided by that magnitude we just found, and then multiply that by vector v. When we do that, we get 1 divided by the square root of 13 times our component form for vector v, which is 2, negative 3. Now this is just scalar multiplication. We have to distribute this scalar through to each component. So our unit vector is 2 divided by radical 13, comma, negative 3 divided by radical 13. To check and see if this really is the unit vector, we could take the square root of our first component squared plus our second component squared. You can grab a calculator to plug this in and check for yourself, but the unit vector, the magnitude of vector u, would be equal to the square root of 2 divided by radical 13 squared plus negative 3 divided by radical 13 squared. If you simplify that, you get a value of 1 for the magnitude of vector u. Next, we're going to talk about directional angles. If vector v has direction angle theta, the components of vector v can be computed using the formula v is equal to, for our first component, we're taking the magnitude of vector v times the cosine of our angle theta. For the second component of our vector, we're taking the magnitude of vector v times the sine of our angle theta. For an example, we want to find the components of vector v with direction angle 120 degrees and magnitude 8. Using the formula, we get v is equal to 8 times the cosine of 120 degrees. For our first component, the second component is going to be 8 times the sine of 120 degrees. Now this is where, if you have a good understanding of the unit circle, it makes simplifying this really quick. The cosine of 120 degrees is equal to negative 1/2. The sine of 120 degrees is equal to radical 3 over 2. So if we simplify our first component, we get a value of negative 4. And if we simplify the second component, we get a value of 4 times radical 3. Now we're to our last example. In this example, we're going to find the direction angle of a vector. So we have vector u, which in component form is negative 2, 3, and vector v, which in component form is negative 4, negative 1. We can see those vectors on the coordinate plane to the right. So we want to find the magnitude and direction angle for each of those vectors. First, we'll start with vector u. Magnitude of vector u is equal to the square root of our first component squared plus our second component squared. So the magnitude of vector u simplifies down to radical 13. Now we're going to use the formula that we talked about in the previous example that relates the direction, angle, and magnitude to the component of a vector. In the problem, we know the components for vector u. So if we want to find the angle theta, we can take our component for that vector and set it equal to the magnitude times the cosine of our angle. So we take the first component of our vector u, which is negative 2, set that equal to our magnitude, which we just found was radical 13, times the cosine of our angle alpha, which we can see by our sketch to the right is the angle we're referring to when we're talking about vector u. Now we want to isolate to get this angle by itself. First we would divide by radical 13. And then after we divide by radical 13 to get our angle alpha by itself, we would have to take the inverse cosine to each side. So if we take the inverse cosine of negative 2 divided by radical 13, you get approximately 123.7 degrees for that angle, which according to our sketch to the right seems reasonable. So now we have to use vector v. First, we need to find the magnitude of vector v, and then use that magnitude so that we can find the direction angle for that vector. The magnitude of vector v is equal to the square root of negative 4 squared plus negative 1 squared, which simplifies to radical 17. Using the same process as last time, we set the first component of our vector, which is negative 4, equal to our magnitude times the cosine of our angle beta. So first, if we divided by radical 17 and then took the inverse cosine, if you take the inverse cosine of negative 4 over radical 17, you get beta is approximately 166 degrees. But we have a slight problem, because if we look at our drawing, we know this on the opposite x-axis represents 180 degrees. Our angle is more than 180 degrees, so 166 is not going to be our final answer. And this is where we have to use ideas from a previous lesson, chapter 4, when talking about the inverse trig functions. Our values for our angle beta, if we're using the inverse cosine, go from 0 to pi or 0 to 180 degrees. So to actually find the measure of our angle beta, we have to take 360 degrees minus this value we got. For angle beta, the direction angle for vector v, we take 360 minus 166 to get approximately 194 degrees for that direction angle, which makes sense. If we're in quadrant 3, we know our angles are going to be between 180 and 270 degrees, which 194 degrees is. The last thing to quickly discuss in this lesson is the difference between velocity and speed. The velocity of a moving object is a vector because velocity has both magnitude and direction. If we would take the magnitude of velocity, that is going to represent speed. This lesson had many new terms and ideas, a lot of new notation, so it might be your benefit to go back and rewatch some of the key parts to this lesson.